you'll recall, in science, information is gathered in an orderly way, and that way is using the scientific method. Now, how does science begin? So let's say you happen to take a look at this picture and you notice you've got some really beautiful blue water, and then out from shore there is this really, really red water. Well, what you're doing is making an observation, and observations use one or more of the five senses. Let's say that you're a scientist and you're trying to figure out what is going on in the water. You're going to collect some data. Now, there's really two types of data that can be collected. One of them is called qualitative. That's descriptive. So noting that the water has turned red, that's qualitative information. Quantitative information gives you numbers, so quantities. So if you wanted to measure the organisms in the water that were turning it red, that would give you a number. That would be quantitative. This is a red tide. This organism grows prolifically in certain environments, usually warmer water at a certain time of year, and it can reduce oxygen levels in the water and can release toxins, so it's harmful to organisms that swim through the water. Sometimes there's confusion about what is an observation and what is an inference. So an observation is just simply something you can see, hear, taste, smell, or touch. And so those are all those five senses I mentioned earlier. So if you're looking at this picture, you would observe that it looks mountainous and that it's a cloudy day, possibly an island. Those are all good observations. Observations can be used interchangeably with your data. And remember, it can be qualitative or quantitative. Inference is trying to explain those observations. What are the likely reasons? Why is it a cloudy day? Here's another simple example. Let's say you have this comic, and on the left, you've got the dog starting to dig into the dirt by the fence. And on the right, it looks like he's coming up out of the ground on the other side of the fence. So based on those observations, you can infer what was happening in the middle was that the dog was digging underneath the fence. So let's do a little practice. The organism has legs that are much longer than its short arms. Observation or inference? Hopefully you said observation. You're observing how long its arms are and legs are. Now let's try this one. The organism has brown fur similar to that of a bear. Observation. The organism probably uses the fur to stay warm in this cold environment. That's an inference. You can observe that it has fur, but the purpose of the fur would be an inference. And then the organism was not aware of my presence because it did not run away. This is an inference. You're observing it didn't run away, but trying to say why it didn't run away, that's an inference. One last one. The organism must be sick because he's barely moving. You're observing that he's barely moving, but you're inferring it's because he's sick. Now, when we use the scientific method, there are a series of steps. Now, it depends on the source that you're looking at as to what the steps are called. Sometimes there's 5, sometimes there's 7. It really doesn't matter, just as long as you get the basic idea down. So let's go through just the basic steps. And we'll start with observations. Let's say that in your house you observed some plants that were growing, and you heard some music playing in the area where the plants were every day. So maybe you inferred that music affects their growth. So from there, you might want to develop a hypothesis that says music affects the growth of plants. Now, the way that you develop your hypothesis, it has to be formal and testable. Sometimes in middle school you had to do the if-then statements. That's fine. And that means it's testable, means you can actually perform an experiment and prove or disprove your hypothesis. Now, let's say that you get a little more specific and make it more testable. And let's say you want to say that rock music will make the plant grow better than classical music. And from there, you're going to design your controlled experiment. Now, in a controlled experiment, you're going to have controls and or constants, and you're going to have some variables. And those variables are called either the independent or dependent variable. Now, for the constants or the controls, the control is your group of comparison. So let's say you have a plant in your experiment that you are not going to expose to music, you're still going to measure how tall it gets, and you're going to keep everything else constant. So all plants in the experiment will get the same amount of light and the same amount of water. They're the same exact type of plants. And then you're going to test whether or not music affects the plant. The independent variable is under your control. And you can think of the I in independent as I am in control of those variables. So you might choose for one of the plants to receive some rock music in the area where it's growing, and the other plant you're going to give some classical music to. Those are both independent variables. You chose them. Now, dependent variables are not under your control. These are going to be the response or the results. Now, once your experiment gets rolling, you're going to make some observations and collect some data. Remember, it can be qualitative or quantitative. In our case, it is quantitative because we're measuring how tall the plant gets. And then you're going to express your data in tables or graphs, which are the graphs are much easier to read than just a simple data table. And here are our results expressed in a graph. Now, once you have your results, you're going to analyze what the data means. You could say, the rock music did not make the plants grow as much as the classical did, so your hypothesis was incorrect. And that's okay. It doesn't always have to be quote unquote correct. And then you're going to develop your conclusion. What are your final results? And then could you improve your design, or could you expound upon your design? All right, so classical music made it grow faster than rock music. How about rap music? Now, once a study is complete, you're up for peer review. And this is where your peers look over your stuff and make sure that you did everything correctly. And one of the things they're going to check for is bias. Scientists must avoid bias at all costs. This is your own personal thoughts that could come into your research and influence how you perceive the data and the conclusions that you draw. A great example of this is Dr. Andrew Wakefield, who was the one that attempted to link the MMR vaccine, which is measles, mumps, and rubella, to higher incidence of autism. His research was published in The Lancet in 1998 and was subsequently revoked a few years later when it came to light that he was going to benefit financially from his findings and that his data could not be replicated in any other laboratory, and also that some of the treatments and procedures he used on his young patients were unethical. Now, something that people often get confused about is what's the difference between a theory, a hypothesis, and a law? Well, hypotheses are just predictions about what you think is going to happen, and they can be revised. And it takes multiple hypotheses to feed into a theory. And a theory explains why a natural phenomena is occurring. For example, the theory of evolution has many decades of research with proven hypotheses that shows that natural selection does occur and can lead to the evolution of species. Now, a law is a set of observed natural phenomena that happen the same way over and over. It doesn't explain why something happens. It just says that it happens this way every time. For example, the law of gravity. If you drop something, it's going to fall to the ground because that's what happens every single time. It doesn't explain why it's occurring. It just says that this is what's going to happen.